Hey everyone! Ever looked at a plane or a wind turbine and wondered just what makes those wings and blades so efficient?
It's a great question. And the answer lies in something called NACA Airfoils.
NACA Airfoils.
Yeah, they've been quietly shaping how things move through the air for almost a century.
Almost a century. That's a long time. I'm already intrigued. So for today's deep dive, we'll be taking a look at some excerpts from a text all about these things.
Oh, that sounds like a great deep dive.
Yeah, hopefully by the end, we'll all be able to decode those NACA numbers you see and understand why they matter in everything from drones to wind turbines.
You know what's really fascinating to me?
What's that?
It's how NACA Airfoils kind of democratized aerodynamic design.
Okay, what do you mean by that?
Well, before these standardized shapes came along, designing a wing was like, well, it was a bit like navigating in uncharted territory.
Okay, so how did these NACA airfoils change all of that?
It's the NCAA numbering system, really.
Right, the numbering system.
It's brilliant in its simplicity.
Oh.
Just a few numbers can tell an engineer everything they need to know about an airfoil shape and what it can do.
You mean its characteristics?
Right, exactly.
Okay, can you give me an example?
Sure. Let's take NSIA 62412.
Oh yeah, I've definitely seen those numbers before. Break it down for me. What does that even mean?
Okay, so the first digit, the 2 in this case, it represents what we call the maximum camber.
Camber.
Camber, yeah. Think of it as the curvature of the airfoil, how much it's curved,
Okay.
and it's expressed as a percentage of the chord length.
Chord length. Remind me what that is again?
Ah, right. The chord length is the distance from the leading edge to the trailing edge of the airfoil.
Ah, got it. Like the front of the wing to the back of the wing.
Exactly.
Okay.
So in this case, with NACA 2412, we have a 2% camber.
So that first number, that gives us a sense of how curved the airfoil is.
Right.
What about that second digit?
Ah, that's important too. That second digit, the forfeit, it tells us where that maximum camber is located.
Where it is along the chord.
Exactly, along the chord. So in NACA 2412, the maximum camber is 40% back from the leading edge.
Got it. Got it. Okay, so the first two digits, they give us the camber and its location.
Right.
What about the last two? What's the 12 all about?
Those last two digits, the 12, well, they reveal the maximum thickness of the airfoil.
Oh, the thickness.
And again, it's a percentage of that chord length. So in this airfoil, it has a maximum thickness of 12% of the chord.
Wow, so much information packed into just 4 numbers.
Isn't that neat?
It really is.
It's like a shorthand code, right?
Yeah.
It lets engineers instantly picture the airfoil shape.
In this system, it revolutionized airfoil design, right?
Absolutely. It made it so much easier for engineers to share ideas, to compare designs, and really just to build on each other's work.
So it wasn't just about the shapes themselves, but about this really elegant system for describing and categorizing them.
Exactly.
Okay, so these NCAA airfoils, they didn't just sort of appear out of thin air, right?
Oh, no, definitely not. They are the product of, well, decades of research and experimentation.
Wow.
To truly understand their impact, we really need to go back to the beginning, the early 20th century, the golden age of aviation.
Okay, let's hop in a time machine. Set the scene for us. What was it like back then?
All right, picture this. It's the early 1900s. The Wright brothers have just made history with their first flight.
Incredible.
Right. The world was captivated by this idea of heavier-than-air flight.
Yeah, and it's amazing how quickly things progressed from there.
It really is. But back then, there was still so much that people didn't know about how wings actually worked.
It must have been an exciting time to be involved in aviation.
Oh, absolutely. It was a time of incredible excitement and, like you said, rapid innovation.
And that's where the National Advisory Committee for Aeronautics comes in.
You got it, man. Founded in 1915.
So what did they do?
Their job was to push the boundaries of aeronautical knowledge.
Sort of like a think tank for everything aviation.
Exactly. And one of their main focuses was understanding and improving how airfoils were designed. They ran countless experiments, testing different shapes and setups in wind tunnels.
So that's how the NACA airfoil series that we know today came to be.
Exactly. And their early work, what we call a 4-digit series, like the NACA 2412 we talked about,
Right.
those are real game changers. They gave engineers a standardized way to design wings.
And those early airfoils, they really laid the foundation for modern aviation.
They did, but Nessie didn't stop there.
Of course not. So what came next?
Well, aviation technology was constantly evolving.
Right.
And so was the need for more sophisticated airfoils.
So as planes flew faster and had to carry more weight, engineers needed airfoils that could handle those demands.
Precisely.
So what did they come up with?
Well, the 5-digit series came next.
Okay, how is that series different?
The 5-digit series really focused on better lift characteristics.
Lift being that upward force that keeps a plane in the air.
Exactly. So the 5-digit airfoils, they were designed to make more lift, especially at lower speeds.
Can you give me an example of a 5-digit airfoil?
Sure. The NACA 23012. This airfoil, it has a higher design lift coefficient than its 4-digit counterparts. This means it can generate more lift at a given angle of attack.
Angle of attack.
Which is basically the angle between the airfoil and the oncoming air.
So you're saying with the 5-digit series, engineers could design wings that were more efficient and could lift heavier things.
Oh, got it.
What came after that?
Well, as aircraft started pushing the limits of speed, especially during World War II, a big concern was drag.
Drag.
Yeah, that force that resists motion through the air. And drag, well, it increases dramatically as speed goes up.
Of course it would have to.
And that's where the 6 series airfoils came in.
So the 6 series was all about minimizing that drag to maximize speed.
You got it. Yeah. These airfoils, they were designed with what we call laminar flow in mind.
Laminar flow.
Laminar flow. It's a smooth, orderly airflow pattern. It creates a lot less drag than turbulent flow. Which is, kind of chaotic.
So it's like the difference between swimming in a calm lake versus a really choppy ocean.
That is a great analogy.
Thanks.
So by promoting that laminar flow, the 6 series airfoils, well, they allowed aircraft to fly faster and more efficiently.
Amazing. So we have all these different NACA airfoil series, each one designed to address a specific challenge in aviation. But, what I find really amazing...
What's that?
These shapes, developed so long ago, they're still so relevant today. It's like they've stood the test of time.
It's a testament to just how ingenious those NACA engineers were.
Yeah.
And to the power of those fundamental principles.
Even with all the advances in computer modeling and simulation today.
Even then, those classic NACA airfoils, they're still a really reliable starting point for many designs.
It's like the foundation upon which all of modern aerodynamics is built.
Exactly. And their influence goes way beyond traditional aircraft.
Really? Like what?
Think about wind turbines, for example.
Okay, those giant blades that capture the wind's energy.
Right, they often use modified NACA airfoils.
Oh, wow. I hadn't thought about that before. So the same shapes that help planes fly are helping us generate clean energy.
Exactly.
That's so cool.
And then there's the world of unmanned aerial vehicles. Drones.
Of course. They need airfoils too.
Whether it's a small drone capturing some aerial footage or a larger one delivering packages, NACA airfoils play a crucial role.
It's incredible how versatile these shapes really are.
They really are.
But before we get too ahead of ourselves, I think it's important to really understand the science behind how these airfoils actually work.
That's a great point.
You mentioned things like lift, drag, and those mysterious coefficients. Can you break those down for us? What are some of the key concepts to really grasp?
Absolutely. To really appreciate why NACA airfoils are so important, we need to take a deep dive into the world of aerodynamics.
Okay, sounds good.
Let's start by unraveling those aerodynamic forces. Lift and drag, and those all-important coefficients.
Okay, I'm ready. Let's do it.
All right, let's start with lift. Lift is that amazing force that allows a plane to defy gravity, to stay up in the air. It all comes down to the difference in air pressure above and below the wing.
So it's something about the shape of the wing that creates a pressure difference? How does that happen?
It all comes back to the shape of the airfoil.
Yeah.
Particularly the camber. Imagine air flowing over a curved airfoil, right?
Yeah.
The air traveling over the top, it actually has to go further than the air flowing underneath.
Makes sense.
And to meet back up at the trailing edge, the air on top, well, it has to speed up.
So the air on top of the wing is moving faster. Okay, so what does that do?
Well, there's this principle called Bernoulli's principle, and it says that faster moving air exerts less pressure.
Ah, interesting.
So because the air on top of the wing is going faster, it creates a low pressure zone above the wing compared to a higher pressure zone below the wing.
Ah, I see. And that pressure difference, that's what creates lift, right? It pushes the wing upward.
You got it. Now, the amount of lift generated depends on several things. The shape of the airfoil, the angle of attack, and the airspeed.
And that's where the lift coefficient comes in.
Precisely. The lift coefficient, it's a number. And it tells us how well an airfoil generates lift.
So higher lift coefficient means more lift.
At a given angle of attack and airspeed, yes.
It's like a measure of the airfoil's lifting power.
Exactly. Now let's talk about drag for a minute.
Drag.
Yeah, that's that force that resists motion through the air.
Yeah.
We always want to minimize drag.
Makes sense.
Because it's basically stealing energy and making things less efficient.
Drag is the enemy.
You could say that, yeah. Drag comes from friction between the air and the surface of the airfoil. Even though air seems invisible, it's actually made up of tiny molecules.
Right.
And as those molecules hit the surface of the wing, they create friction.
So the smoother the surface, the less drag, right?
Yeah, that's one factor, yes. But the shape of the airfoil matters a lot too.
How so?
Remember that curved upper surface that helps create lift? Well, it also adds to the drag.
Right. Makes sense. So there's like a trade-off between lift and drag.
There is.
You want enough curvature for lift, but not too much to create drag.
Exactly. That's why engineers spend so much time optimizing these designs. They're trying to find the sweet spot.
Get the most lift with the least drag.
That's the goal.
I bet that's tricky.
It is. And just like with lift, there's a coefficient that measures drag.
The drag coefficient.
Right. A lower drag coefficient means less drag at a given speed.
So we want a low drag coefficient
Yeah.
and a high lift coefficient.
Exactly.
Okay, I think I'm getting this.
There's also the moment coefficient. It describes the rotational forces acting on the airfoil.
Okay, so moment is about rotation. Why is that important?
Well, engineers need to consider the moment to make sure the aircraft is stable and controllable.
Makes sense, I guess.
Imagine if an airfoil made lots of lift, but it also had a strong pitching moment. It could make the aircraft nose up or down uncontrollably.
Ah, that would be bad.
It would be.
Okay. So these coefficients, lift, drag, and moment, it's like the language that engineers use to understand how an airfoil will behave in the air.
That's a great way to put it. They help engineers to analyze and compare different designs, optimize performance, and basically predict how something will fly.
And you also mentioned something called boundary layer theory. What is that all about?
Ah, yes. The boundary layer is where things get really interesting. It's that very thin layer of air right next to the airfoil surface.
Okay.
And what's cool is that in this boundary layer, the air behaves differently than the air further away, what we call the free stream flow.
So it's like the air that's stuck to the wing almost. Why does it behave differently?
Because of friction. Friction between the air molecules and the surface. Right at the surface, the air velocity is actually zero.
Zero. So like the air is sticking to the surface and then it gradually speeds up as you move away from the wing.
Exactly. And that change in velocity within the boundary layer, it creates these shear stresses, and that contributes to drag.
So even though the boundary layer is super thin, it has a big impact on drag.
A very big impact.
So what can engineers do about that?
Well, the behavior of that boundary layer can either be laminar, that's the smooth one we talked about before,
Right.
or it can be turbulent, the one that's more chaotic. Understanding how and when the flow transitions from laminar to turbulent, that's critical.
So that's where boundary layer theory comes in.
It does. It lets engineers design airfoils that minimize drag and maximize efficiency.
I see. Do you have a real-world example of this?
Sure. Have you ever wondered about those dimples on a golf ball?
Yeah, actually. Do they have something to do with this?
They do. Those dimples are strategically placed to manipulate the boundary layer and reduce drag. That's what makes the golf ball fly further.
Wow, I never realized that. Dimples on a golf ball.
It's a great example of how understanding that boundary layer can lead to some really innovative designs
Yeah.
in unexpected places.
Okay, so we've talked about all these forces and coefficients and boundary layer theory. This stuff, it's not just for rocket scientists, is it?
Oh, not at all. These concepts, they're fundamental to understanding how anything moves through air or water.
Really?
Oh, yeah. Whether you're designing a drone, a wind turbine, a car, even a high-performance swimsuit.
Wow.
All of these principles come into play.
It's amazing to think that these shapes, like NACA Airfoils, have unlocked so much knowledge about the world around us.
But they really have.
And I'm sure as we continue to push the boundaries of technology, understanding these fundamental principles will only get more important.
Absolutely.
Well, this is really fascinating. I can't wait to dive even deeper into these NACA Airfoils.
Yeah, I'm excited too.
We'll need to take a quick break, though, and let all this information sink in. We'll be back soon to continue our deep dive. Stay tuned.
Welcome back. I don't know about you, but my head is spinning a little bit with all this talk about NACA airfoils.
It's definitely a lot to take in. It is. We've talked about their history, the numbering system, the different series. We've even gotten into the physics of it all, the lift, drag, those boundary layers.
It's a deep dive for a reason.
It is. But I want to hear more about their applications today. Like we touched on before the break, those wind turbines and drones.
Right.
Where else are we seeing these classic shapes making a difference?
It really is amazing how shapes developed for early aircraft have made their way into so many different fields.
It is.
One area where NACA airfoils are having a huge impact is renewable energy,
Oh, interesting. Tell me more about that.
specifically wind power.
Wind turbines. I know they use airfoils to catch the wind, but I'm curious about the blades themselves. How are they designed?
That's a great question.
Are they using those classic NACA shapes right out of the book? Or are they tweaking them?
Well, those classic NACA airfoils are a great starting point, but engineers are always looking for ways to make things better. They're constantly refining those shapes to optimize them for specific uses. And when it comes to wind turbines, there are some interesting challenges.
Challenges, like what's different about designing an airfoil for a wind turbine compared to, say, a plane?
Well, think about the size of those turbine blades. They're huge. Some of them are over 200 feet long.
That's massive. That's longer than the wingspan of a 747.
It is. And designing an airfoil that works well at that scale is no easy task.
I can imagine.
Engineers have to think about things like structural integrity, material strength, and how those blades interact with the wind at different speeds and from different directions.
Wow, that's a lot to consider.
It is. And there's another big difference: how wind turbines operate compared to airplanes. A plane wing, it's designed to make lift and move the aircraft forward.
Right, in a controlled way.
Exactly. But wind turbines, they're stationary. They got to capture energy from wind that's constantly changing.
So it's not just about lift. It's about harnessing the energy of the wind.
You got it. To do that effectively, you got to think about the airfoil shape, the twist of the blade, how those blades are angled to capture the most energy from all those different wind conditions.
It's a lot more complex than just sticking a basic NACA airfoil on a pole.
Oh, for sure. Engineers are using some really sophisticated computer models to analyze and fine-tune those shapes. They're often inspired by those classic NACA designs, but with some really interesting modifications.
It's like a blend of old and new, isn't it?
It is. It's those fundamental principles we talked about before: lift, drag, boundary layer theory, applied to a cutting-edge technology.
It's pretty amazing. It really shows how powerful those basic principles are.
It does. And it's a great example of how smart people are using them to solve some of the world's biggest challenges.
Okay, so we've talked about wind turbines. You mentioned drones earlier, too, as another area where NACA airfoils are playing a big role.
Right.
What can you tell me about that?
Well, the world of drones is just exploding right now. We have those tiny ones that fit in your hand and can do all kinds of cool tricks.
Yeah.
And then there are the big ones, the ones that can carry heavy loads over long distances.
And they all rely on the same basic principles of aerodynamics that we've been talking about.
Absolutely. But just like with wind turbines, the airfoils on drones are often tweaked and customized to meet specific needs.
Okay, so what kind of things do they have to consider when designing airfoils for drones?
It really depends on what the drone is designed to do. What's its mission?
Right, that makes sense.
For example, a drone that's used for surveillance, it might need to stay in the air for a really long time. So you'd want an airfoil that minimizes drag and has a good lift-to-drag ratio.
So it's using as little energy as possible.
Exactly.
But if you're talking about a racing drone, that needs to be fast and maneuverable.
Right. Then you might need an airfoil that can handle high angles of attack and quick turns, even if that means sacrificing some efficiency.
So again, it's about trade-offs.
Finding the right balance for the job.
Just like with the wind turbines.
Exactly. And just like with the wind turbines, those NZA airfoils are often the starting point. But engineers are always modifying them, fine-tuning them to get the best performance for that specific drone.
So whether we're talking planes, wind turbines, or drones, it all comes back to those fundamental principles.
It really does. It's amazing, isn't it?
Mm-hmm.
Those NCA airfoils, developed almost 100 years ago, they're still so relevant today.
They're everywhere.
They are. It's because they embody those core principles of how things move through the air.
It's a real testament to those early aerodynamicists.
They really laid the groundwork for everything that came after.
It's inspiring to think about how those shapes are still informing these new innovations.
It is.
In all these different fields. Renewable energy, unmanned flight. Who knows what's next?
Makes you wonder what those pioneers would think if they could see how their work is being used today.
I know. I bet they'd be blown away.
I think so too. They'd be thrilled to see how those basic principles they uncovered are shaping the world. And I'm just as excited to see what the future holds. For airfoil design, I mean.
Okay, let's talk about the future. What are some of the exciting things coming down the pipeline?
One thing that's generating a lot of interest is morphing wings.
Morphing wings? What does that mean?
Imagine a wing that can actually change its shape while it's flying.
Wow, that sounds like something out of science fiction.
It does, a little bit.
Does it really work?
It's getting closer all the time. Researchers are working with things like flexible materials and complex mechanisms to create wings that can smoothly transition between different shapes.
So a plane could take off and land with one wing shape for more lift, and then change to a more streamlined shape for cruising?
Exactly. That's the idea.
Uh,
And it could completely change aviation as we know it. More fuel-efficient planes, quieter planes, more versatile planes.
that's incredible. What else is going on?
Another really cool area is bio-inspired design. Biomimicry, it's called. Basically, engineers are looking to nature for inspiration. Studying how birds, insects, even fish, they've developed some really efficient and maneuverable ways of moving through air and water.
So we're learning from the experts.
Exactly. By studying nature, engineers are getting all kinds of new insights that they can use to design everything. Drones, wind turbines, even underwater vehicles.
So the same forces that shaped a bird's wing over millions of years are now inspiring engineers to design new tech for the 21st century.
That's the idea. It's this beautiful combination of science and nature, working together to drive innovation.
I love that.
And then you have the incredible advances in computer modeling and simulation. With the computers and software we have today, engineers can test and refine their designs virtually.
Before they even build a physical prototype.
Right. They can explore so many more possibilities, test them under all kinds of conditions, optimize for performance in ways they never could before.
It's like a virtual wind tunnel.
It is.
So we've got morphing wings, bio-inspired designs, super powerful computer simulations. It sounds like the future of airfoil design is pretty bright.
It really is. And as we push for things like efficiency, sustainability, better performance, those core principles we see in those ANSI airfoils, they're going to keep guiding us.
They really have made a lasting impact.
They have. And I think it's because they represent this timeless legacy of ingenuity and human exploration. We're always trying to understand the world around us.
It's been an incredible journey, exploring the history, the science, the future of these amazing shapes.
I agree.
But I think we need to take a short break here, let all these ideas settle in. We'll be back soon to wrap up our deep dive into NACA Airfoils. Welcome back to our deep dive into the world of NACA Airfoils. We've covered so much ground today, from their history to their modern uses, and even a peek into the future of airfoil design.
It's been quite a journey.
It has. But before we go, I want to bring it back to you, the listener.
It is important to think about what all this means for our audience.
Exactly. Whether you're an engineer or just someone fascinated by how things work, there's something here for everyone.
Absolutely. If you're intrigued by the idea of building things that move through NACA airfoils, and the principles of aerodynamics are a great place to start.
There are so many resources available these days. Online, in libraries.
You can find detailed papers, simulations, even software where you can experiment with different designs.
It's amazing what's out there. You can test out different shapes, see how they affect lift and drag, all virtually.
It's like having your own wind tunnel.
Mm-hmm.
And you never know. Maybe you'll be inspired to design and build your own flying machine.
A model airplane, a drone, even a kite.
Understanding those principles we've been talking about can make a world of difference.
And even if you're not planning to build anything yourself, understanding aerodynamics can change how you see the world around you.
I totally agree.
The next time you see a bird flying, you'll think about the forces that keep it up there.
Or, if you see a sailboat, you'll understand how the wind and the shape of the sails work together.
Even something as simple as a flag flapping in the wind.
It's all aerodynamics.
It's like having the secret code to unlock the forces that shape the world.
That's a great way to put it. Knowledge really does open up new perspectives.
It does. And it helps you see the world in a new way. So we encourage you to keep exploring, keep learning, never stop asking questions.
The world of aerodynamics is full of amazing things just waiting to be discovered.
Who knows, maybe one of our listeners will be the next great innovator, the one who makes the next big breakthrough.
It all starts with that curiosity, with asking what if.
What if we could design a wing that changes shape in flight? What if we could build drones that are as efficient as birds?
These are the questions that lead to new discoveries and new technologies. And I think the things we've talked about today, the history, the science, the possibilities, they'll inspire you to keep asking those questions.
So as we wrap up this deep dive into ANSI airfoils, we want to leave you with one last thought.
Those classic shapes, they're a reminder of human ingenuity. They've had such a huge impact on our world.
And they're still inspiring us today. But that's just the beginning. The future of aerodynamics is wide open.
It is. And we can't wait to see what you discover. Keep exploring and keep learning.
Thanks for joining us on this deep dive. Until next time.